Okay, good afternoon. We can now start with the afternoon session. Okay, so we will now have the third lecture of Laura Donnet on celestial amplitudes.
Thank you, Francesco. Thanks everybody for coming. Good afternoon. I hope you can hear me in the back. Yes. Okay, so today we will finally come to talking about celestial amplitudes per se, after these two first lectures where we had to make a detour to understand what was the detailed structure of the flat space in the infrared, and we saw these nice symmetries and that they had charges and that these charges were constraining the scattering problem for massless particle in flat spacetimes. And today we will see, so we will go to now the definition of what celestial amplitudes, and we see that this essentially amounts to have a very nice organizing way, very nice way of organizing scattering elements in flat spacetime, which will make the SL2C transformation of the Lorentz group very manifest. And these eventually will help us to understand what is the potential holographic structure of gravity, quantum gravity in flat space in terms of the so-called celestial conformal field theory. So let me recall briefly what was the last message of last lecture. So yesterday, I tried to advocate that there was a nice interpretation of soft photon, and we mostly discussed actually soft graviton insertions in the quantum gravity S matrix. As a word identity, for some two-dimensional currents. And these 2D currents manifest the rich asymptotic structure at the boundary of flat space. So for gravity, we had these currents were given by super translation currents, which I will come back to it when we will talk about celestial CFT. We will come with a nice definition for this current. We also had for gauge theory this U1 Kac-Moody current, which is whose insertion is responsible for the leading soft photon theorem. This guy gives you the leading soft graviton theorem. And I mentioned, and we will come to a concrete construction for this object, but that there is an object which plays a role of the stress tensor in very much like we are used to in usual 2D conformal field theories. So that was the main message of yesterday. And today we will now go to the core of these lectures, which is to talk about celestial amplitudes. So let's, in order to present you this celestial map that maps the particle states to objects in the 2D sphere, let me just briefly introduce some aspects about Lorentz transformations and the celestial sphere, which I recall is the two-dimensional Euclidean sphere at future null infinity, which is antipodally identified with the past null infinity. So we have, let me write down the Lorentz algebra. Just to start slowly. where I use the notation J, I, so I is 1, 2, or 3. J's are my 3 rotations. K's 1, 2, 3 are the 3 boosts. And these are the commutation relation between these objects. And we are also very, well, we know that there is an isomorphism between the Lorentz algebra and the SL2C algebra, which is also something you have seen in other lectures here. So the Lorentz generator are here denoted by the usual LMs mode. And this is their commutation relation. Where M and N are also -1, 0, 1. And okay, there is a precise way how to obtain this L in function of the rotation and boost generators. Let me not write all these down because you can find this in most of textbooks, but let me just write one of these relations, just have an idea. Okay. So now we will need, and actually I've already kind of introduced that in the previous lecture, but we'll make a choice for an embedding of how the celestial sphere is embedding into Minkowski. So of the celestial sphere into actually the null code. So there is no unique way to do that, but there is a nice form of the embedding which I can take, and I've already actually introduced that when we were talking about scattering of massless particle, and this is the choice for, if you remember, the particle has this momentum p mu, which I written omega, the energy times this null vector yesterday. So we have seen this expression already before, and it gives me an embedding of the celestial sphere. And of course, there is not, you could make another choice for this embedding, but this one turns out to be very convenient for all these celestial amplitude purposes. So now the key observation which is behind all this story is very simple. It's just the fact that the Lorentz group acts on the celestial sphere via a Möbius or SL2C transformations on these sphere coordinates W and W bar. Okay, where is the usual SL2C transformations similarly on W bar. So this is just a symmetry observation. ED minus BC equal to 1.
Oh, sorry.
Yes, yes. Yes, yes. So now by using this just simple observation, and I will come to precisely how one can perform this map explicitly. If I write the S matrix element into a basis which expresses in a manifest way the SL2C invariance or covariance that acts on the celestial sphere, then by construction, these objects written in this sort of basis will transform covariantly in the reaction of SL2C. And this is precisely what we are aiming at. We are aiming at eventually interpreting these S matrix element in this basis. And again, I will just now define how you can perform this change of basis. So by construction, you will have this SL2C manifest transformation laws. And celestial holography or celestial amplitudes is the statement that we will want to interpret these elements as a correlation function, so something totally different of operators which represent the massless particle in a theory, which is this so-called celestial conformal field theory. So that's the main goal of what's the main objective of this transformation that I will present now in more detail, talking about conformal primary wave function.
Laura, sorry, stupid question. So N is the number of particles involved into the scattering?
Yes, thank you. Yes, sorry. So basically, the usual so someone is unmuted, I guess, online. So the usual drawing that people do is that if you have a scattering process involving n particle, here n equal to 5, you will see or reinterpret this thing as some correlation function as insertion of operators. So each operator here, operator, which represents massless particle which pierces the celestial sphere at a point, the given point W bar. And the delta will come to it, but it will be the dual variable of the energy. I will precisely come to that. So you will see this scattering process as some insertion of operators. So if you have 2 incoming and 3 outgoing, they will all live on the same celestial sphere. So this follows from the fact that, remember, we had some antipodal matching between the past and the future. In principle, you might think there is one celestial sphere at the past and one at the future, but this antipodal matching is precisely made in such a way that these 2 regions are identified to each other in such a way that a free massless particle will enter and exit the celestial sphere at the same point. So this all comes from this antipodal matching condition I've written. The main message is that there is only one celestial sphere, and we will have insertion of operators which represent creation of, well, a massless particle coming from the past and versus at a given point the sphere, W bar, and we have n of them in principle.
So this correlation, can it be interpreted as coming from some specific null coordinate? Because presumably the scaling dimensions refer to the Fourier transform in the retarded or advanced null coordinates, right? So in some sense, they are smeared all over scri minus or scri plus.
This dimension is not quite the Fourier transform of the neither the energy nor there is a Melon transform associated to that, and I will come to this precise mapping.
I see. But right I mean, does it correspond to strictly local insertions on some?
No. As you say, it involves at the end an integral over all retarded times.
I see. So it's there's some smearing.
Yes, there is some smearing. You're right.
Thank you.
So, okay, let's go to this map. I mean, what is this delta? How is it defined? So conformal primary wave functions, abbreviated by CPW. So let's, so all the magic will be done by this integral transform called a Melon transform. So let's consider again a non-shell plane wave. Can be incoming or outgoing. Plus or minus I omega q mu x mu, where x are the Cartesian coordinates. So here plus or minus is in versus out. So as we have seen, we can parameterize the null momenta by three quantity, the energy and the point WW bar at which the particle passes the sphere. And this Melon transform that will make the magic for us, namely trading the omega for this delta. And this is how the celestial map is implemented. So Melon transform, the definition of this transform is as follows. An integral transform over a variable that is here will be the energy on the particle. So this is the Melon transform of a function f, which depends on omega. It returns a new function, which now depends on this variable here that appears in the integral transform. That's the Melon transform. There are some assumptions on this function f for the Melon transform to be well defined. If you're interested, you can go in. You can ask me reference for this, but I don't want to enter into too much detail. So delta in principle can be is generally complex in this expression and take so this form. And I will come back to that. So in principle, delta is an arbitrary complex. There is a well-defined inverse transform. So you can invert this Melon integral modulo some assumptions. But there is a way to invert this map. So notice that there is an inverse Melon under some assumption. It's about the analyticity of this f tilde on some complex strip. We will not need all these details, but just to tell you that you can go back and forth under some assumption. Okay. So what I will call a conformal primary wave function is simply a Melon transform of a plane wave packet. So let me start with so now I'm starting with a scalar conformal primary wave function. So this is a definition of what I mean. So we'll have a bunch of labels, so we have to be careful about all these labels because we don't want to neither confuse you nor be too sketchy. So a conformal primary wave function, which can be incoming or outgoing, depending on whether the plane wave is incoming or outgoing, is defined as the Melon transform of the wave packet, and it will carry. Now, it will no longer be labeled by energy omega, but rather now by this quantity, this complex delta. So I'm just writing this Melon transform for a plane wave. And this epsilon here, just some regulator, which is there to ensure that the integral converges, which is positive. So that's the definition. Let me introduce some stupid extra label that is not necessary here, but when we'll be talking about spinning wave functions, we will have to introduce another label, which is spin. And here, since I'm talking about scalar conformal primaries, this label will just be dumb and just be equal to 0. But in general, we can define more general spinning primaries. So this integral can be computed. Actually, you can. In mathematics, it just gives you what's the answer. And the result is given by this, where you have this appearance of this regulator here in the denominator. So it's plus or minus I to a delta gamma function of delta divided by q dot x to the power delta. So why are we interested into this? Well, because now the nice thing about these functions, as their name suggests, is that phi transforms now as a bulk, as a scalar under the bulk Lorentz transformations. So you see that this object depends both on the bulk coordinate x and also on point w bar on the sphere. It's just a scalar under the Lorentz, but under the action of the Lorentz, which is induced by this embedding, so on this SL2C action acting on w bar, it transforms, as you will see, a 2D conformal or quasi-conformal primary. Because now I'm just looking at the global part of the conformal group with the given weights, like the weights that we are used to write down into the CFC, H bar, under SL2C. So I will write down the transformation rule so that this sentence takes some flesh. So if I do a Lorentz transformation on the coordinate, which is accompanied by a Möbius transformation on the angles w bar, and then I could have just written down w prime, w bar prime. The transformation rule that you can check that this is true. And there are two ways of expressing the weights, either in terms of H and H bar, either in terms of the conformal dimension and the spin, and they are related via this equation. The conformal dimension, as usual, is the sum of H and H bar, while the spin, the 2D spin, is the difference. So here it's actually 0, but when we will generalize this to spinning particles, it will no longer be 0. So equivalently, this is actually well, if you're more familiar with this way of writing the conformal transformations, here is an equivalent way of writing that. So you should recognize this as the transformation rule of a primary of weights H and H bar. Is it clear? So what we are just doing is we're making this integral transform on the plane waves. And this the reason why we are doing that is because now we have made the SL2C action manifest. So in summary, usually we write in a momentum basis where particles are labeled by their energy. Here in this boost, or let's call it celestial basis. Particle will be represented by this complex number delta. And we go from one to the other via this Melon transform. And if we have a spinning particle in the bulk, it will carry a, so that's the energy. It will carry a helicity L. And this will be simply identified with the 2D spin in this. This will be equated. So this is 2D spin on formal dimension. Okay. So now there is a comment I would like to make, which turned out to be rather important. Before I write that, maybe I just mentioned that this phi delta, another way to state this is just that they are complex now, highest weights with respect to the Lorentz group. So this is just another way just to write down what the weights are. So since this is a scalar, 0, they satisfy these relationships where these L are the Lorentz generator I've written before. Okay. So basically, now the action of the boost is diagonalized. While in the usual momentum basis, we have the plane wave transform manifestly nicely under translations, but the SL2C transformation is obscured. Now it's the other way around. We will have in this boost basis, the transformation under SL2C will be very nice. But now the price to pay is that the transformations under translations will be more obscured. And I will get back to that later on. Is there any question on that? Yes.
I have two questions. First of all, this action of SL2C on W can be just derived from the definition of the complex coordinate on the celestial sphere?
Up to, well, there is no unique way that this will induce a unique way to write this down. So this will depend on this embedding. So it's actually equivalent to choose the little group, choice for a little group. But if you give, if you give me a given embedding, then yes, you can derive this. You can derive this in a unique way.
Okay, so okay, but okay, this two coordinate, the W is essentially does not contain more information than X, no? It's just a way to parameterize the limit for the distance going to infinity.
Yes, so the Lorentz group will accompany the transformation on the bulk coordinates will induce a transformation on the angles at the sphere at infinity. So they go hand in hand.
Okay, so but I'm not understanding why when you write the fields, you write both X and W, like if they are independent coordinates.
Well, so in principle, it's like, you know, a plane wave in principle depends on the bulk point at which is defined, but also has a momenta which is pointing towards a point in the sphere. So if you want here also, this plane wave is also an object which depends both on X and on this Q. But now this Q, I'm choosing an embedding which where this Q is parameterized by WW bar.
Okay, okay.
So it's the same stuff, but now in this basis somehow. It's just we are not used to that because we are not used to write the null momenta, I guess, like so, but there's nothing.
Okay, so the W is the large distance limit of the dual variable of X.
Yeah, exactly.
Okay, okay.
So exactly. So this object is defined at any bulk point X. But now I will want, so it's a bit what we did yesterday when we pushed this wave, this function to the boundary by taking a large R limit. And then I mentioned this saddle-prone approximation computation that I didn't show. But basically, when you will push this to the boundary, it will make, the angles, let's say Z here, which are included, in boundary coordinate, you have UR, Z, Z bar. It will make Z and Z bar to coincide with W and W bar.
Okay.
When you take the larger, you're right. Yes, I know it's a bit, might be confusing, this double thing, but it's nothing but, again, if you look at the plane wave, just inherited from this and this relation. So now let me make a comment. So the statement that plane waves form a delta function normalizable basis, which is statement where these things denote the Klein-Gordon inner product. I can write down quickly the definition I'm using for the Klein-Gordon two massless stuff. So we are familiar with the fact that the plane waves form a delta function normalizable basis, which express like so. Okay. So this statement translates into the celestial language in the following way. This statement will impose some constraint on the value of delta. More precisely, what you can do is just, you take this expression here, you do two Melon transform, one for the first plane wave, one for the second, and you will find the Klein-Gordon inner product of two primary wave functions. Let me just write W, and not every time W and W bar, but so there is one evaluated that depends on W, one on W prime. So it can be in and out. So if you do a Melon transform, the two Melon here, you can compute this. So the left-hand side is equal to that by definition of what is informal primary. But at some point, you will hit some integral, and you will see that this integral doesn't converge unless you restrict delta and delta prime. So you can see here, this guy depends, a priori can depend on, can carry another conformal dimension delta prime. So it will constrain delta and delta prime to take this form. Where lambda is and lambda prime are real. And you've encountered similar stuff in Matthias' lecture before. So these are the continuous here it's called the principal series of irreducible representation of SO 1,3. So this is imposed by the convergence of the Melon integral. And this is something that was worked out by Sabrina Pastersky and Shuhang Shao. Maybe I can give you some reference, by the way, for these conformal primary wave functions. So I guess Dirac already looked at this, but more recently they were investigated by Debout and Solodukhin, and also Pastersky, Shao, and Strominger, 2017. Here's the reference for that. And you can find the reference for the Debout-Solodukhin paper inside this paper. So basically, this statement about the delta function normalizability of the plane waves is translated into the Melon basis as some restriction on the conformal dimension to lie on the principal series. So I will come back to that because there are a lot of subtleties about this spectrum, if you want. But I think this is something that is worth mentioning, because actually these modes, these celestial primary wave functions, which have these values of delta, correspond actually to normalizable states which have a usual radiative fall off when they go to the boundary of space-time. But in general, you might wonder what happens if I go off the principal series. So if I take the real part of delta to be 2, for instance, and these are also a very interesting thing to look at. As we will see, the stress tensor obviously lies outside this principal series, and we will come back to that when I will talk about tomorrow about 2D currents. Any questions or comments? Okay, I guess this is just not a question, but just a microphone left open. Otherwise, I didn't understand the question. So let me say a few things, few comments about now spinning conformal primary wave functions, because at the end of the day, we'll want to discuss scattering of photons, gluons, and gravitons. So spinning. So this was, I've written here the scalar case. Formal primary wave functions. So spin 1 first. They equal plus or minus 1. So now the confusion is arising because there will be some plus or minus coming that mean plus or minus helicity, and there are some plus or minus which meant outgoing and incoming. I will actually now I will suppress the in and out labels. Because otherwise we will have too many indices to carry on and rest. So a spin 1 primary wave function will carry now well, it would be we'll have some tensor indices. And let's see, let me write it here. So J equal +1. So I'm looking at helicity plus here. So it has spin J equal +1. So it is defined, roughly speaking, as a scalar conformal primary times these tetrad M mu. And there is I will explain that, but let me just write down the expression for the negative helicity, just to be complete. So now J is equal to -1. We'll have a M bar now times the scalar conformal primary. So this carries the helicity piece, and you might think that I could have obtained a spinning primary just by multiplying the scalar by the polarization tensor, but this is not quite true. This M is not the polarization tensor. It is the polarization tensor of plus helicity. This is the notation that I used yesterday. Corrected or shifted by a quantity that depends on the bulk coordinate x. And this q mu times q dot x. And similarly, M bar gives you the object for the opposite helicity. So again, here plus and minus, they don't denote incoming or outgoing, but the helicity. So these things are required in order to have a nice transformation under SL2C. If you just take this polarization tensor times the scalar primary, you will see that this guy doesn't transform nicely under SL2C. You have actually to take this tetrad thing. And so now with this, spinning one primary, so transforms under Lorentz and the Möbius. Now it will be also transforming as a 2D primary of weights H and H bar. But now it's also transforming as a vector under the bulk transformation. Okay, so this is the same transformation as for the scalar, except that now it's transformed as it should under the Lorentz action. Notice that there is some intrinsic gauge fixing into this definition. I don't want to mention too much on that, but basically these guys, are naturally in Lorentz gauge, but just because of the equation satisfied for the scalar primaries. And similarly, and then I will stop bombing you with definitions, but we have a spin 2 primary, which is plus or minus 2. And this will define for us later on the currents that play a role in celestial CFT. So for plus helicity, this is nothing, but now you need to take 2 of these M's here. And similarly for J1 minus 2, where you take the bars. And now these guys will transform as a tensor under the Lorentz group. And it satisfies so this thing satisfies the linearized equation of motions. So yeah, basically, if it's in the so-called the Donder gauge, this will just be box of h min equals 0. Yeah, a bit more complicated if you relax the trace and the Lorentz condition on it, but yeah. So just to finish, so it's an important thing that the fact that to have this nice transformation, you have to add this piece will make this object quite not equivalent to just the polarization tensor times the scalar 1, but they will actually be gauge equivalent to that. But we have heard in the first lecture that the gauge, all that has to do with gauge, we have to be very careful because there are some gauge transformation or diffeomorphisms that do not die at the boundary, and we have to keep track of all that. And actually, it will be crucial to keep these gauge transformations because some of them can be non-zero at the boundary. And so just to tell you that the relationship between simply the polarization tensor times the scalar primary, these guys is gauge or diffeomorphic equivalent to it. So I'm not writing the explicit expression for xi mu. You can find it in the Pastersky paper. The exact form is not very important, but you can already see that there are weird thing happening when delta equal to 1. So for this value of the conformal dimension, you can see that the naive spin 2 conformal primary is no longer well defined. It just reduces to a pure diffeomorphisms. And this is actually tight and in one-to-one correspondence with the presence of super translation and of this super translation current that I have presented yesterday. And I will go back to it. So here I just want to say, watch out when delta equals to 1, and also when delta is equal to -1, but this I don't want quite to discuss this. When delta equals to 1, this guy is a pure diffeomorphism, or sometimes called a Goldstone mode associated to the breaking of super translation symmetry. So far, it's not clear why this has to do with super translations, but I wanted to mention this already at this stage. And similarly for the AMU, so the AMU is gauge equivalent to epsilon mu times the scalar guy. Right, and the factor is delta -1 over delta. So you can see again that delta equals 0 and delta equals 1 seem to be important value of the conformal dimension. And indeed, this guy will define for us some Goldstone mode associated to the breaking of large gauge transformation at the boundary. So now this alpha gauge can be large. Namely, it doesn't die at the boundary, gauge transformation. Again, watch out when delta equals to 1. And this will actually define for us what people have been calling a conformally soft operator in celestial CFT for these specific values of delta. Any question? For now we have all the relevant quantities and transformations to talk about celestial amplitudes, to define celestial amplitude. The last 10 minutes.
Sorry, I didn't quite understand. Are you saying that all A mu's are gauge equivalent to that particular form? With delta minus 1 over delta?
So this is an exact statement, this. This is just, so what I mean is that this A mu, so this is just an equality that follows. If you take, remember the expression for phi delta was roughly speaking 1 over q dot x to the delta times some I and some gamma of delta. So if you take this and multiply it by that, you will be able to write it in this form. So the first term will just give you this piece, and the other guy, I'm sorry that I'm not sure I have the expression for alpha here. Oh yes, I have it, so that you can check if you want that you agree with this, but the expression of alpha is just epsilon times x divided by delta times minus q dot x to the delta. So this is just an equation you can check easily. What I meant is that this A mu is not exactly equal to epsilon times the scalar 1, but is gauge equivalent to it. They just differ by gauge transformations, but usually we don't care about gauge transformation. We just say, yeah, I mean, we drop these. But as we have seen in the first lecture, there are some gauge transformations that are non-zero at the boundary, and they act non-trivially on the states. So we better keep them. And indeed, we'll see that this will define for us when delta equal to 1, these 2D currents that I call GZ.
And the point is you need that extra term for you to transform nicely in the SL2C.
Yes, exactly. So it's because if this guy doesn't transform in a nice way, but this object does.
Thank you.
Yeah.
Okay. Do you also get like a funny 0 at delta equals to 2 in some other thing that you have the super translations, no? To somewhere.
Yeah, so the special value for us will be 1, 0, and 2. So delta equal to 2, as you might guess, will has to do with the stress tensor for the graviton conformal primary. And the delta equal, did you ask about delta equal 0 or?
Delta equal 2, I think it is the super rotation, was this called the Virasoda thing.
Delta equal 2. And then I will mention this shadow transform, which exchanges delta with the 2 minus delta. So the delta equal 2 and delta equal 0 are related with a shadow transform.
Okay, thanks.
I will define what is a shadow transform tomorrow. Good, so in the last 7 minutes, we can finally find what is celestial amplitude. So basically, we have already encountered that, but okay. So a celestial amplitude, 3.3. So if I write a usual S matrix element, these are the usual momentum basis. So we talk about state somehow, and now we'll talk about wave functions. We'll talk about amplitudes of n particles. Now we have a precise way. Before I was a bit sketchy, but now, so we have a precise way to define that. So as I've said over and over, massless particle is parameterized by an energy, a point that the bar twisted versus the sphere. And this is the helicity. So this is the usual way we express amplitudes in this momentum basis. So for massless, actually, yeah, I'm focusing on massless case. Maybe I will say a word on massive case. The celestial amplitude is, so I will call it curly C now, involving n particle, will be labeled now by two other quantum numbers, this conformal dimension and the spin. And it's just defined as taking n times the Melin integral, one for each leg of the usual momentum basis amplitude. So where here the identification between the L and the J is just really in the identification between the helicity and the spin, as I have mentioned before, and we trade the energy for this delta. And this is definition of a celestial amplitude. For the massless case, this map is simply defined with the Melon transform. But for a massless case, it's a bit more tricky, but there is also a way to make an integral transform, which is such that the scattering of massive particle will always transform nicely under SL2C. So for write this in words. So this is just to go a little bit beyond what I have presented so far, where I focus only on massless particles. There is, so the map involves now no longer the Melon transform, another transform. Which is built from the tool from a CFT embedding formalism and involves the bulk to boundary propagator from ADS propagator. So this is just a common if you're interested into the massive case, which I have to say is much less understood from a celestial holography perspective than the massless case. So I'm just writing down the reference for that. If you're interested in looking at this, how you can obtain a celestial amplitudes for massive particles. But so the important point and the upshot of all this is that for both cases here, so this is another, not a Melon. What I meant is not a Melon transform, but something else. But for both cases, by construction, celestial amplitudes transform covariantly under SL2C. This meaning again that if I act with SL2C by design, I will have an N for endpoint function. Well, m times these sort of factors, where the h's are the weights of each associated to each scatterer. Okay, so hi is, again, it's just delta 1/2 delta I bar delta I minus GI. Okay, so what you can do now that you have this recipe to build celestial amplitudes, you can take any formula for your favorite amplitude. And the first one that were computed in the celestial basis were the 3-point maximally helicity violating gluon amplitude. And I will not write down this because I'm running out of time. But just so that you have an idea of what it looked like, you can really explicitly compute, check that the amplitude you obtain. So example, 3-point MHV gluon amplitude. You can do the exercise. This is the reference for the paper. You do 3 Melon transform, and then you get, so you start from the amplitude you know from the formula, and then you obtain that the celestial amplitude for, let's say, 2 minus helicity and 1 plus gluon. So there are subtleties you have to go in the split signature because, and take Z and Z bar real and independent, but basically you will find sort of expressions that you recognize as a 3-point function in a 2D CFT. There are some subtleties that I don't have time to discuss, but you can ask me. There are some delta function in the Z bar coordinates. This is inherent to these low point functions. You can ask me more on that, but you recognize this as the usual form of a 3-point function with the given weights. This is the standard expression with definite weights where these lambdas. So remember that delta I. So here they are also lying on the principal series, and delta I is 1 plus I lambda i's. And this is just, and then I'm done writing. This, the specific form it takes, so you can actually check for a bunch of amplitude that performing this integral makes all this CFT looking like transformation to be very manifest. So this has also been checked for massive particle and for other sorts of particle, but I will just stop here. So thanks very much for listening.
Thank you very much, Laura.
And we also discussed a little bit about the topological string, which we propose will be holographically dual. So today, we're going to study the back reaction in the topological string. At least that's the first thing we'll study. So last time we wrote down the field sourced by a brane in the topological string. This was a certain Beltrami differential. When we solve that equation, the geometric role of the Beltrami differential is that it changes the Cauchy-Riemann equations. So in our case, in the deformed geometry, the original coordinates were W1, W2, and Z. And here, the new Cauchy-Riemann equations are these equations here, which tell us what does it mean to be a holomorphic function in the deformed geometry. So let's solve these equations, and then we'll find that the deformed geometry is ADS3 times S3. Let's go up a little bit. So if we look at the equation, nowhere in the equation is there a d by dw1. So w1 and w2, these are still solutions to these deformed Cauchy-Riemann equations. So these still define homomorphic functions. However, if we look in the equation, we see that there's a d by dz. So the function z will no longer be holomorphic. You can instead see that there are two new holomorphic functions, which I've called u1 and u2 here, given by these expressions. u1 is zw1 plus n over normal w squared w bar 2. u2 is something similar. And it will take you half a minute to stick u1 and u2 into these equations and check that these equations are solved. So w1, w2, u1 and u2 are the holomorphic functions in the new geometry. However, they're not independent. As you can see, u1 w2 minus u2 w1 is equal to n. Which is again entirely elementary. So we conclude that the deformed geometry is that defined by this equation. So we can think of this as the space of 2 by 2 matrices, like this, with column vectors u1, u2, w1, w2, whose determinant is n. Now I can absorb the factor of n into a rescaling of some of the coordinates. So you might as well think of this as matrices, its determinant is 1, so that the geometry is SL2C. Okay, so this is the topological string derivation of the back reaction. For the experts, I want to point out that this is a little simpler than what normally happens in the physical string, because we don't have to pass to any near horizon limit. Once we back react, the geometry already has a homogeneity, which means passing to the near horizon limit does nothing. Okay. Well, are there any questions about this computation? No. Okay, so our goal is, of course, to compare the chiral algebras we've been discussing to quantities built from the topological string in this deformed geometry. So if we go back to think about the more familiar ADS5 times S5 holographic dictionary, the very easiest thing you might see is that in ADS5 times S5, the symmetries of the CFT are the same as the isometries of the geometry. This is a very basic and elementary check, the ADS CFT correspondence. So, well, the isometries of ADS5 times S5 are SO6 times SO42. And here, SO6, that rotates the 6 scalars of n equals 4 Yang nodes. And SO4,2, that's the conformal symmetries of the fourth sphere. And the symmetries of the fourth sphere which preserve the metric up to available scaling. So because it's a CFT, these are symmetries of n equals 4 Young-Mills on the fourth sphere. So what we're going to do in the twisted holography setting is we're going to check that this statement holds. But what we will find is that it's a much richer statement for us because the group of symmetries will become infinite dimensional. And therefore will give us a very, very strong constraint. So before we move on, let me explain briefly how to think about the symmetries in the case of the CFT in a more abstract language. Your CFT will have a certain number of conserved charges, especially in a chiral CFT. Any operator gives you a conserved charge. I integrate it around a circle, that's my conserved charge. However, we're interested in those conserved charges which preserve the vacuum at 0 and at infinity, like that. So if I take my charge, integrate around the 3 sphere, and I hit it with the vacuum at 0, I get 0. Similarly with the vacuum at infinity. So think of these as the initial and final states. So maybe just want to add another page. Why is this a good thing to do? So charges like this preserve all correlation functions. So you can have a picture like this where I have local operators. And if I sum over integrating a charge around the local operators, that's going to have the same effect by change of contour argument as integrating the charge around all of them. That's going to be 0 because it is the same as integrating my charge against the vacuum at infinity. Okay, so we'll come in a minute. We'll come back to calculating these symmetries in the CFT side. So back to the topological string side. What will be the analog of the isometries? Well, we know that general relativity is covariant under diffeomorphisms. And of course, diffeomorphisms are the gauge symmetries of general relativity. And the isometries are those gauge symmetries which preserve the field configuration you start with. Like they preserve the vacuum field configuration, which, the metric on ADS5 times S5. So the kind of thing we will study that will replace isometries will be gauge symmetries preserving the vacuum field configuration. So let's study what that is. Let's look in the type 1 case. So the fields, the solutions to the equations of motion more precisely, from the closed string sector, there's a complex structure and a homomorphic volume form. And from the open string sector, we have an SO8 bundle, a holomorphic SO8 bundle. So what are the gauge transformations of this data? Well, for the complex structure, that's really a part of the metric. So the gauge transformations are diffeomorphisms. Those which preserve the vacuum field configuration, though, because we don't have all of the components of the metric, we're not just looking at isometries, we're looking at those diffeomorphisms which preserve the complex structure. And they also have to preserve the volume form. So at an infinitesimal level, diffeomorphisms are given by vector fields. So these are holomorphic and divergence-free vector fields on SL2C. So if you're familiar with complex geometry, you might notice that this is a very, very, very large Lie algebra. And we're going to see it, that it also appears in the CFT side. Something that's a little easier to study is what happens for the open string fields in the type 1 string. There we have, our gauge field describes a holomorphic bundle on the manifold. So those gauge transformations, which preserve the holomorphic structure of the bundle, are not constant, but rather they satisfy this equation. So the gauge transformations are holomorphic maps from SL2C to SO8. So again, this is a very big space because there are lots of holomorphic functions on SL2C. So these Lie algebras are infinite dimensional. So our goal today is to find these Lie algebras in the chiral, inside the chiral algebra as symmetries which preserve the vacuum at 0 and infinity.
I have a question.
Yeah?
So since SL2C is non-compact, is there some condition on the holomorphic vector fields at infinity that one has to impose?
No, you look at all of them.
Okay.
So that's why it's so big, you see. Okay, so let me try to write a little more explicitly what the open string algebra is. We're looking at holomorphic functions from SL2C to the Lie algebra SO8. So what kind of thing is that? An element of it is going to look like a product of an element of SO8. A is an adjoint index for SO8, and a holomorphic function on SL2C, which is a function of the variables ui, wi, modulo the equation u1, w2 minus u2, w1 is n. So let's look at the quantum numbers of these symmetries. How do they transform under the natural kind of evidence symmetries one has? Well, of course, under the global SO8, these expressions live in the adjoint representation. What's more interesting is to think about how these expressions live under the left and right action of SL2 on itself. So the group SL2 acts on the left and the right by matrix multiplication. So on the CFT side, we also have those two SL2 actions. The left one is the global conformal symmetry, rotates CP1. So this is kind of the analog of SO42. And the right one, it rotates, in our theory, we have two matrices and they have a symmetric role. This right action rotates those matrices. So this is the analog of SO6. Now, how does a function on the group behave under the action of left and right multiplication? Well, fortunately, there is an old theorem from the 1920s or something, which tells us this. This is really just harmonic analysis of the group, the compact group, if you like. But it says that every homomorphic function can be expanded to modes, and the modes live in the tensor product of the spin J representation on the left with the spin J representation on the right. So our symmetries are then in the joint of SO8, tensor spin J on the left, spin J on the right. Okay, and so we should keep this in mind because we want to reproduce this from the CFT side. Well, when we want to identify the algebras we see on the topological string of the CFT, we also want to identify them not just as vector spaces, but also the structure constants of those algebras. So let's write down some structure constants as well, and then we'll see if we can reproduce them on the CFT side. Oops, I know that comes later, sorry. Take that back. I will discuss the structure constants later. So what we'll do now is find symmetries with exactly these quantum numbers in the CFT. So how does that work? So if you remember in the CFT, the elementary fields are 8 vectors and 2 matrices. And these matrices have certain symmetry properties. And the gauge invariant operator is going to be interested in, the single trace ones are vector, bunch of matrices, vector. Because of the symmetry properties of x1 and x2, this expression is anti-symmetric in the OR-S indices, so that it's in the adjoint of SO8. And under the conformal symmetry of the CFT, this is an expression of spin m plus n over 2 plus 1, because the i's and the x's are all of spin half. Now, it also lives in some representation of the SL2, which rotates x1 and x2, and it's in the representation of spin m plus n over 2 of that SL2. So we've listed the open string operator and which representations it lives in. But to reproduce the quantum numbers we saw on the holographically dual side, we should recall that we're not interested in all operators or all modes of operators. Rather, we're interested in those modes that preserve the vacuum at 0 and infinity. So this picks out a subalgebra of all of the modes. Some people call this the wedge algebra. So how is this defined? If I take the contour integral of some operator, I take some mode, you ask, okay, when does this preserve the vacuum at 0? For that, you need k to be positive, like non-negative, because if k was negative, then I hit it with the vacuum at 0, I'm going to get some derivative of my operator. And then you ask, does it preserve the vacuum at infinity? Well, we change coordinates. Z goes to 1 over Z. And I pick up some powers of Z from the way the operator transforms, which is dictated by its spin. And you find it preserves the vacuum at infinity if k is in this range, where J is the spin of my operator. So for example, if I had a spin 1 operator, then only that is in the algebra. Sorry, I think I need a. Page to explain this. So spin 1, like an ordinary current, JA, so the globe, if I have a spin 1 operator, maybe it satisfies a Cas-Moody OPE, then the global symmetries will be a finite dimensional Lie algebra. I have a spin 2, like the stress energy tensor, then this constraint tells me that we have naught less than or equal to k less than or equal to 2 j minus 1, and if j is 2, we have k is naught 1 or 2. So for spin 2 operator, like the stress energy tensor, the global symmetries are the SL2 global conformal transformations. As you increase the spin of the operator, you get more and more global symmetries. So let's go back a little bit and see what are the global symmetries of associated to our basic currents. Our basic currents are I, x1 to the m, x2 to the n, I. Well, if you look at the spins, you see k is allowed to be in the range from 0 to m plus n. So these expressions, they're in the adjoint of SO8, of course, and they're in a representation of spin m plus n over 2 with respect to both the SL2 conformal symmetry and the SL2 symmetry which rotates x1 and x2. So this is the same quantum numbers as we saw before. It's like sum SO8 tensor BJL tensor BJR. So if there are no, are there any questions there?
No.
Okay, so what have we seen so far? On the topological string side, we looked at the analog of isometries. We found this big algebra, maps from SL2C to SO8. And on the CFT side, we looked at those modes which preserve the vacuum at 0 and infinity, and we found something which looks the same. At least something that has the same quantum numbers. I haven't explained how to calculate the quantum numbers of the closed string operators, but it's not hard to check that they also match. So what we haven't done so far is match the structure constants of these Lie algebras. So the way it's going to work is that here T is some element of SO8. I'm writing this for ORNS or vector indices for SO8, and things are anti-symmetric in ORNS. So homomorphic functions from SL2C to SO8, they look a little like this. At the lowest level, I just have those constant functions here, which are these. Then I have those functions which are linear in the coordinates, TRS-UI and TRS-WI. These are going to get sent to IXI. The distinction between the UI and the WI is whether or not there's a Z, DZ, or just a DZ. And the same happens as you go down. So we need to be able to match the non-trivial commutators. So let's examine one of these commutators. For example, if I take TRS times U1, TPQ times W2, and I commute them, all I'm doing is I'm taking the SO8 commutator of these matrices. These are anti-symmetric matrices. I'm just commuting them. And then I'm multiplying the functions. In particular, if I specialize these indices to particular values, you find T12 U1, T23 W2 is U1 U2, U1 W2 T13. Similarly, T12 U2, T23 W1 is U2 W1 T13. But now we should recall that SL2C as a defining relation where U1 W2 minus U2 W1 is equal to N. So we get such a relation in the commutator, like this. So this is the relation we're going to want to match. So let's translate this into the CFT language. U1 is going to be a mode of X, I1, X1, I2, like this. And W2 will be like this, an X2 and a Z. And the other commutator, there's going to be an X2 with no Z and an X1 with a Z. And we expect that the modes commute according to this relation. And we're going to do this computation in a minute. And we find it works. Well, what I find kind of cool about it is that it's a way, here we're just doing some computations in the mode algebra of the CFT, and we're seeing that holomorphic functions on the dual geometry appear, like the defining relations. Okay, so let's go and do this computation. So before we do so, I think I should remind people of something pretty elementary, about how one does, how do you commute elements of the mode algebra of some chiral algebra. So in general, if I have two operators in a 2D CFT, O1 and O2, I can take their modes with some powers, e to the k1, e to the k2, and I can try to commute them. So the commutator is just the difference between two contour integrals, where here, on this contour here, O1 is on the inside, and O2 is on the outside. And this contour here, O2 is on the inside, and O1 is on the outside. Now, when I take the difference between those two contour integrals, you can write it as a contour integral where here O1 moves around in a circle and O2 orbits around O1. So to write that in coordinates, we're going to do contour integral of Z, just go around in a circle, and a contour integral of W, also going around in a circle, but O2 is placed at Z plus W. And then I also have to have this power of Z plus W to the K2. Okay. Now, when we do the W contour integral, what kind of non-zero terms can we find? Well, of course, we're only going to find terms which have a power of 1 over W, because you want to get a residue. Expanding this expression will give us positive powers of W, and the OPEs here will give us negative powers of W. So we see that the terms that are relevant are the terms in the OPE, which have a first order pole, second order pole, up to a pole of order K2 plus 1. Okay. In our case, we're doing a commutator of something here where there's no powers of Z and something here where there's 1 power of Z. So by this argument, the commutator will have terms from where there's a first order pole in the OP between the two operators or a second order pole. Now, in our CFT, the OPEs involving a pair of elementary fields always has a first order pole. So like a wick contraction contributes a first order pole. Since we want a first or second, we find that the relevant terms involve 2 wick contractions. So let's write out diagrammatically everything that involves 2 wick contractions. Here, I can contract x1 with x2. But this is bad, because this is a non-planar diagram. So since we're looking at the CFT in the planar limit, this will not contribute. I can contract I1 and I2. That's good, and that contributes this expression to the commutator of the modes. Or I can contract x1 and x2 and I1 and I2. So, and I2 and I2. And this will contribute something with an n, and I1, this should be an I3. This will contribute n, I1, I3. And the reason for the n is, in the usual large N combinatorics, when I have a loop like this, here, it contributes a factor of n from like the trace in that loop. So I think, so now we've pretty much gone through the proof. If I commute these guys, I get I1, X1, X2, I3, Z, DZ, and a factor of n. For the other one, you find the same thing and minus n, I1, I3. So you find pretty much the same thing except for an extra sign. So we see in the algebra the analog of the commutation relation, of the defining relation of SL2C by commuting the modes past each other. Okay, so this is really easy, but fun. So any questions? Okay. So how does it work more generally? So the theorem is that the global symmetry algebras for the planar CFT at the topological string are isomorphically algebras, even when you include the closed string sector. So let me say a little bit about this. So the general case.
Maybe I can ask you a question, actually.
Sure, yeah.
So on the chiral algebra side, if I understand correctly, we don't have to take large n, right? We can understand this chiral algebra at finite n with small n. Where do we see the need for a large n to match with the topological string? I mean, here we had a match, but we've dropped the 1/n corrections in non-planar diagrams. So where would we see those corrections?
Right, so this gets into things which are a little tricky, but possible to do. With involving, you can try to compute by various methods. So the diagram we dropped looks like this. These are contracted here. But these go off like that. So it's like a 2-to-2 scattering process. I haven't drawn it very well. So that's the way to draw it. And one can compute. So there are one loop corrections to the OPE in the topological string, and these capture it. So it is possible to see it, but it's a little tricky. So I think in general, you know, I like to be optimistic and think that loop corrections on the topological string side should be much more accessible than they are on the physical string. And I think they are, but they're still not easy. And probably the best way to approach them is to note that they're very tightly constrained by crossing symmetry.
Okay, thanks.
Of course, the other way and large n appears is that there are trace relations. And I don't know how to see those in the topological string at all. Okay, so in general, statement is that if I take some kind of open string thing like this, the planar ones, I have to contract a bunch of adjacent stuff. Some other ones go off. That. This is a 2-to-1 kind of open string process. in CFT that if we're looking at the global symmetry algebra, that this matches the Lie algebra, holomorphic maps, from SL2C to SO8. And similarly, on the closed string side, we take modes of this guy in the global symmetry algebra, match vector fields, holomorphic, convergence free, vector fields on SL2C. So how would we prove this? So for the open string side, we're done. Because the algebra is generated by TA, TAUI, TAWI. So really, once we've checked this commutation relation, algebra, basically the Jacobi identity, so on, tells us the two algebras must be the same. Well, what about the closed string side? That's going to be much more challenging. Well, on the CFT, it's more challenging to do the CFT computations. We're going to use the following trick. Vector fields on SL2C are derivations of functions on SL2C. And so I'm going to use this symbol for functions. And so there's symmetries of this Lie algebra. And on the CFT side, you can kind of see explicitly why the closed string fields have to be symmetries. But if I take a closed string field like this, the commutator of this with an open string field looks like, do these go past? This kind of thing. And you can check this kind of, well, this is compatible with the Jacobi identity. So I've kind of very briefly sketched why the argument we just gave. Well, very simple. It is enough to allow us to constrain, just using algebra, all of the symmetries, and to see that for the closed string side too, we also get vector fields on SL2C. Okay, so the topic I haven't talked about so far, let's see, which I'm going to have to go spend more time on tomorrow, is states from the point of view of holography of the topological string. So in general, ADS-CFT our fields have an asymptotic boundary condition on ADS. So suppose we write ADS in Euclidean signature as like the upper half plane, then roughly there's the fields one wants to consider have some prescribed pole in the radial parameter or. So a local operator is a modification of this asymptotic boundary condition at a point on the boundary. So, which means away from this point, we're going to have usual asymptotic behavior. And at this point, we're going to have modified asymptotic behavior. So I don't know if this is a familiar picture to people, but it relates to the more standard one by saying that, so equivalently, if we modify the boundary conditions, we can find a solution to the equations of motion with the modified boundary condition. So this solution to the equations of motion is the state on ADS corresponding to a CFT operator. So I want to explain how to implement this in the case we're considering of SL2C. So to understand this, we need to think about what does SL2C look like near its boundary. SL2C is like U1 W2 minus W2 U1 equals N. That's up. So to understand the boundary, let's make these into homogeneous coordinates. And then the equation will be U1 W2 minus W2 U1 equals N V squared. So now I'm lifting everything into homogeneous coordinates and then writing SL2C as an open subset of a quadric in CP4 as I'm opposing this quadratic equation. So, just like it started life as a solution of a quadratic equation in C4, and I'm adding on some points at infinity to C4 to get CP4, then I want to see what the boundary of SL2C is in this compactification. The boundary divisor is a locus where V is 0, in which case the equation looks like U1 W2 minus W2 U1 is 0. This is a quadric in CP3. Well, as you might have seen in Anna's lectures, this is kind of standard in the study of scattering. Quadrics in CP3 are parameterized by CP1 times CP1. So the boundary looks like S2 times S2. Now, should we think of this? Well, ADS3 times S3 is SL2C. The boundary so 1S2 is the boundary for ADS3. The other is, well, almost the S3, it's S3 modulo U1. So they're related by a Hopf vibration. Okay. Well, I didn't get very far with the discussion of states. So I told you what it means to get a state. We're going to modify the boundary conditions. Now we've studied the boundary of SL2C, and we find it's a product of two CP1s. So the next thing to do is to look at the boundary conditions and to see that modifications of the boundary conditions do indeed give you the states of the dual CFT. And then after that, we can study we can try to study scattering amplitudes and match them with correlation functions. Okay, so I'll stop there.
Thank you very much.